In this lecture, we look at the concept of continuity at a point. So, intuitively, we can think of it this way, that f is continuous at x naught if the portion of the graph near the point x naught, f of x naught, if that can be drawn without any break, then the function is continuous at x naught. The function is not continuous, or it's discontinuous at x naught, if the graph at x, f of x naught, has a break. Okay, so if we look at this function, at the point x naught, the graph has a jump, and we would say that this function, whatever the function is, this function is not continuous, or this function is discontinuous at x naught. Now, if we look at another point, say where the axes cross, then there is no break in the graph, and we would say that the function is continuous at that point. Okay. You should know the continuity properties of some of the common functions. Sine, cosine, polynomial functions, the exponential function, they are continuous at every real number. The function 1 over x is continuous everywhere except at x is equal to 0. If you think about drawing the graph, there's a break at x equals 0. Or we say that it's discontinuous at x is equal to 0. Okay, so consider this function, the Heaviside function. It maps reals to reals, and for negative reals it takes the value 0, and for non-negative reals it takes the value 1. So there's a break in the graph at x is equal to 0. It's discontinuous at x is equal to 0, and it's continuous everywhere else. Okay. Now, a proper mathematical definition of continuity. So a function that maps u, a subset of the reals, to v, a subset of the reals, is continuous at x naught if all three of these conditions hold. First, the function should be defined at x naught. Second, the limit as x goes to x naught should exist. And third, the limit at x naught of f of x should be equal to f of x naught. So if all three of those conditions hold, then the function is said to be continuous at x naught. If any one of these three conditions fails, then the function is not continuous, or it is discontinuous at x naught. Let's look at a few examples. We have a constant function. F of x is equal to c, for c some constant number. So is f continuous at x is equal to 2? Well, let's check the three conditions. F of 2 is equal to c, so the function value is defined. The limit value is also c, so the limit exists at x is equal to 2. F of 2 is equal to c, which is equal to the limit value at 2, and therefore f is continuous at x is equal to 2. Consider another one. F maps reals to reals defined by f of x is equal to x. Is f continuous at x is equal to 2? Well, we check the three requirements. F of 2 is equal to 2, so the function value is defined at 2. The limit as x goes to 2 of f of x equals the limit as x goes to 2 of x, which is equal to 2. So the limit value also exists. The limit value and the function value at x equals 2 are the same. Therefore, f is continuous at x is equal to 2. Okay, the absolute value function can be defined like this. F of x equals x for x non-negative, and f of x equals minus x for negative x. So consider if f is continuous at x is equal to 0. So we check the three conditions. F of 0 is equal to 0. So the function is defined at x is equal to 0. Now when we check the limit at x is equal to 0, the form of the function changes at x is equal to 0. So we will do directional limits and then check if the regular limit exists. So the limit as x goes to 0 from the right of f of x equals the limit as x goes to 0 from the right of x according to the definition of the function, and that's equal to 0. The limit as x goes to 0 from the left of f of x equals the limit as x goes to 0 from the left of minus x, that's the form of the function for negative numbers, and that limit is equal to 0. So, because the two directional limits are the same, the regular limit exists and is equal to the directional limits. So the limit as x goes to 0 of f of x is equal to 0. Okay, so the function is defined at x is equal to 0. The limit value also exists at x is equal to 0, and the limit value and the function value agree with each other. So therefore, f is continuous at x is equal to 0. Okay. Let's consider another function. Again, this is a function which jumps at x is equal to 0, so I don't expect it to be continuous. We check the three requirements. F of 0 is equal to 1, as it's defined. The limit as x goes to 0 of f of x equals the limit as x goes to 0 from the right of 1 is equal to 1, and the left-handed limit as x goes to 0 from the left of f of x equals the limit as x goes to 0 from the left of 0, according to the form of the function, and that's equal to 0. So the directional limits disagree with each other. That means the regular limit does not exist, and if the regular limit does not exist, then the function is not continuous at that point. Okay. Finally, I'll leave you with this problem. Supposing you have a function from reals to reals. It's defined by g of x equals x over x, for x not equal to 0, and it's defined to be c, some constant number, when x is equal to 0. Now I leave the choice of c up to you, and I ask you to find a c such that when the value of c that you pick should be such that g will be continuous at x is equal to 0. Okay, I leave you with that problem.